Okay, I'm back. And share screen. Oh, hey, that worked. Yay. All right. So in theory, you're about to see my iPad screen. Let's get this to work. Okay, that's good. 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 Yay. All right. Do you all see my iPad screen? I'm going to draw something. Everybody see that?
Yep.
Yep. Good. Cool. All right. Hey, we're in business. Okay. So hold on a second here. Let me get the chat window back up in case anybody wants to chat. And okay. Cool. Hey, we can start class. So before some people joined, since then, since I started, I had asked at the beginning that people leave their video on with their microphones off, just so if you want, you could raise your hand, or I can see if you're reacting to what I'm saying and if I'm making any sense. If you're not comfortable with that, if your room's a mess, or if you've got people running around behind you you don't want me to see, I understand. You can keep your video off. But it'd be nice to see everybody. And this way also helps see everybody else, I think. And if you keep your microphone off, that just helps the sound quality. But feel free to just turn it on at any time and just interject with a question. And if you can also, if you want, chat, you should be able to use the chat window to ask questions as well. So we can try this any number of ways. It's going to get us a while to figure all this out. And on top of all this, I was going to start recording. I think I am recording. I am recording. Okay, good. So it looks like I'm recording right now, and this entire class will get posted in a private YouTube channel. So in the future, if you miss class, or if I say something and you're got distracted because there's a lot going on around you at home, then you can always just rewatch the video. I'll send out the YouTube links to these classes, and then you can hopefully go back and rewatch things. And then obviously, you know, this is all new. This is my first online class I've ever taught right now. So, you know, any feedback you all have to make this work better for all of us, just let me know. Otherwise, we're just going to kind of jump into it and just pretend things are normal as much as we can. So we left off in chapter, let's see my book here, we left off in chapter 3. We've gone through sections 1 through 5 in chapter 3. The last thing we did was repeated and zero eigenvalues. And you have some homework, web work assignment that I assigned before break. It had been due during our break, but then it was due like last week when we weren't supposed to be on break. So I pushed back the due date to tonight at midnight. So if you didn't finish it, you still have an opportunity to finish that. And as usual, I can start the class by just asking if there are homework questions. Does anybody want to ask anything about that last homework assignment?
Question, actually.
Yeah, sure. Shoot.
Can you hear me? All right, cool.
Yeah.
Okay, so I looked up like like the step-by-step solution for how to do the thing that we did last class, which is like when you have repeated eigenvalues.
Yeah, that's the hardest case. Yeah.
The process that I found online was like a little bit different, and like WebWork was taking those answers, but like the answer that I kept getting from like our process was a little weird. So you find like the general eigenvector by doing like v1 is equal to a minus lambda. Can you guys hear me?
I can hear you. Yeah.
Alright, cool. Sorry. You do like a minus lambda I times v naught, right?
Okay. Yeah.
But like the thing I found online had like v1 and v naught flipped, and then yeah, there's like some like minute details.
Yeah.
That were different, and I was like confused. So, like, do you mind really quickly like going over like
Yeah,
what
we can go over it.
the
No, I don't mind at
general?
all. No, it's a good idea to kind of review where we were at. And that is the hardest case, I think, just because it's so different than the other cases. I don't think it's the hardest algebraically. I think complex eigenvalues is probably the hardest algebraically. But I think conceptually, this case is really different than all the others. Yeah, so let's see. Let's see if I can get my technology working here. So we're talking about a situation where we have a matrix and we have repeated eigenvalues. So we've got lambda, not working, and lambda. So we've got two eigenvalues that are the same. So let's see, I don't want to write that. So we're talking about a case where lambda 1 equals lambda 2. And um, I mean, if you just look, so this is so just as a reference here, if you just look at page 319 in the book, and it's right toward the top, you'll see the word theorem. And we spent a full class day on this, but really what it boils down to is just looking at that theorem, and it gives you instructions on how to do it. So I mean, what it says there is that if that the general solution looks like e to the lambda t times v0 plus t e to the lambda t times v1, and they tell you right off the bat that v0 is your initial condition. And you can get v1 by looking at your matrix minus lambda I times v0. And it'll turn out in this case that that v1 is an eigenvector, but you don't have to worry about that. v1 will always be an eigenvector. So it's worth saying. And if all you care about is just what the picture looks like, this part is actually kind of important, because if all you care about is what the picture looks like, I mean, in general, the generic picture is you've got these axes, and then you can just solve for lambda and an eigenvector, just as we always did. It's the same, algebraically, it's the same process, right? And then you plot your eigenspace, there's corresponding to your eigenvector. And then if lambda is positive, things move away from the origin. If it's negative, things move toward the origin. And then all of the other things, this was the in-between case, in between a sink and a source just moving away from the origin or toward the origin, and things that spiral. So in general, things will look like this. You get this sort of S-shaped thing. Why is it doing that? And things move like that. What are you all seeing now? Are you seeing my iPad screen with me drawing on it? Or are you seeing the video, or are you seeing both? Do you see all the videos like in the corner or something? And then somebody want to just chat and answer to that question? Or are you seeing, okay, Ezra says both. Robert says you're seeing the iPad screen. Okay, I've got two screens up. So I see all your little videos on one of my screens, and then I see my iPad video on the other screen. So I don't know what you all are seeing, but you can, when I ask you yes and no questions also, you could just give me a thumbs up, thumbs down, because I see your video for those of you who have the video enabled. Oh, yeah, I like Amber. I like the thumbs up emoji. That's good too. I meant an actual physical thumbs up, but that's good too. The emoji's fine. Okay, cool. All right. Did I answer your question, Suresh? You know what's also awesome about Zoom, I just realized, is that I see all your names over all the video, because I still can't remember anybody's names in any of my classes. So now I can actually call you by your names because you're all tagged with your names. It's going to help me a lot. It's the one advantage.
Yeah, that did answer my question. I kind of had like a follow-up question real quick.
Yeah.
So I was plugging in like v naught as an eigenvector instead of like the initial condition,
Oh, yeah.
and then when you put v naught into that equation to find v1, you always get the zero. Is
Oh,
that like?
honestly, I don't know what happens if you do things in the wrong order. You probably do get something that's
Cool.
kind of algebraically interesting, but I don't know. I'd have to think about it. Yeah.
Interesting. I see.
Anybody else have questions on web work or just anything else we've done? We're going to do a little bit of a review. We're skipping the next section of the chapter, which is 3.6. And then 3.7 will kind of serve as a simultaneous review of everything and sort of a distillation. It's kind of a big picture of what everything, all these different special cases look like. Are there questions specifically to web work? Are we good? Good?
There's a question in the chat.
In the chat. Oh, thank you. Could we cover problem 5 on web work? Sure. So let me pull it up. 5 on web work. Problem 5. Oh, as you're saying, you don't have your microphone or video because my laptop is broken as of now. Yeah, let me know, all of you, if you're having any technical troubles. So no worries. Ezra, it's fine if you just want to chat your questions. As long as somebody points out that there's something on the chat, then I'll know. Problem 5 says, consider the initial value problem. So my version, I'll just write it out. My version says y prime equals -3, 1, 0, -3. And obviously, you all know my handwriting sucks. So if I write something that you can't read, just let me know. I'll try to be a little bit better. It's totally different writing on an iPad versus writing on a blackboard. Okay, and then they're asking, find the eigenvalue, an eigenvector, and a generalized eigenvector for the coefficient matrix of this linear system. And then find the most general real valued solution to the system of linear equations. This obviously came out of a different book, and maybe I should have looked at it a little more carefully before I assigned it, because I don't know what they mean by a generalized eigenvector. Did any of you figure that out? Did any of you do this?
It means v1, I believe.
Oh, the V1, okay. All right.
Yeah.
Well, I'll tell you what.
I looked it up.
You worked it out. Let's just
Yeah.
go through the solution here, and we can do part B, and then maybe after part B, we'll figure out what's supposed to be there in part A. We want to find the eigenvalue. So we just do this as usual. We just start. Crap. That's me resting my palm on my iPad. All right, so we've got -3 minus lambda, 1, 0, -3 minus lambda. And we're going to take the determinant of that. That gives us -3 minus lambda squared minus 0 equals, we're going to set that equal to 0. So our solution to that is just lambda equals -3. Somebody yell or stop me if I made an algebraic mistake. Okay, so now we've got, do they give us an initial condition? They do, right? Here's the initial condition right up there. So if we just do things the way they tell you to do things in the book, V0 is your initial condition. So we've already got this much of it, right? We've got e to the lambda t, we know what lambda is, and we know what V0 is. Okay, and then all that's left is to find out V1 by using this equation down here. So we have to do a minus lambda I times V0 to get V1. So again, V0 is just our initial condition, -2, -1. And then V1 is going to be A minus lambda I. That's exactly this matrix, but now we know what lambda is. So it's minus 3 minus lambda I. What is that? This is going to be kind of silly. What do we get if we do minus 3 minus lambda I? Right, here's lambda. And if we do minus 3 minus negative 3, we get plus 3. We still have the 1, the 0, and minus 3 plus 3 again. Okay. And then all of that, we're going to multiply by V1 to get, sorry, by V0 to get V1. And so that's just the matrix 0, 1, 0, 0 times minus 2 minus 1. And that's negative 1, 0. So if we just follow this algorithm in the book, we're supposed to, the general solution, big Y, is supposed to be V0 e to the lambda t plus, sorry, let me write that the way the book does. E to the lambda t V0 plus t e to the lambda t V1. Okay, and so that's now lambda is negative 3, right? So we've got e to the minus 3t times v0, which is minus 2 minus 1, plus t e to the lambda t times v1, which we just figured out was minus 1, 0. So that should be the general solution. And I think I'm missing, yes, I lied earlier. I didn't copy this down appropriately. I'm missing, what am I missing up here? What's missing from that? What don't I have that's super important that I should have had for the general solution? You could chat it or just yell it out with your microphone.
Is it C1 and C2?
Yeah, I'm missing the constants, right? This should have been C1 times that plus C2 times that. Good, right? So going back down here, I should have had C1 and C2, C1 and C2. So now I'm looking at the WebWorks screen again. They want a solution that looks like C1 times something plus C2 times something. And those two somethings are vectors. So we get C1 times minus 2 e to the minus 3t and minus e to the minus 3t plus C2. They just want something in this form. Minus t e to the minus 3t, 0. So that should be in the second part of the part B of this problem. I don't think I need to share that. So that should answer part B of the problem. Part C of the problem, they just want y1 and y2. So y1 is going to be c1 times minus, well, what do they want? No. They want to know what happens when t equals 0, right? Because we need the original initial value problem. This is the general solution. What are C1 and C2 if we want this initial condition of minus 2 minus 1?
Is it just going to be 1, 0?
It should just be 1, 0. Let's work it out and see what happens, right? We want y of 0 to be equal to -2 minus 1. Okay. And so that has to equal C1 times -2 e to the 0 minus e to the 0 plus C2 times, now t is 0, right? So this is 0 up here. So we just get 0, 0. And so what do we get? -2 minus 1 equals C1 times -2 minus 1. Okay, and that tells us that C1 equals 1. And we can take C2 to be whatever we want, actually. So we might as well take C2 to be 0. And so, yeah, the original solution to the original system should just be this part of it up here. Y1 should be -2 e to the -3t, and Y2 should be -e to the -3t. That should work. So I'm going to type that in and make sure I'm not doing something crazy. Does this agree with what you guys did? I'm seeing a yes. Cool. Okay. And -e. Check answers. Well, it's actually telling me my answer is wrong. So
Yeah,
why?
when I use the process that we just went over, it doesn't give me the right answer either.
Huh. But some people are saying that they did get the right answer. So what are we doing wrong here? Let's figure this out. Oh boy. All right. I'm not sure. I'm stumped. I'm stumped. Let me stare at this a little offline later, and then I'll email you what I come up with. And if I can't figure it out, I'll just pull it off the homework assignment. I'm not sure. Anybody have any quick ideas before we move on to something else?
I think when I was solving it, there was a different process online where you had to, when I found the eigenvalue, I set it equal to the matrix A minus the eigenvalue times I multiplied by the vector that I'm trying to solve. And so then I think that was the generalized eigenvector. And so then from the answers that I found online, you had to multiply like t times the what would that be? The eigenvector.
Yeah.
But then you had to add it to the generalized eigenvalue. If that makes sense. It seems slightly different than what you told us, but it's still like the process is basically the same.
Right.
I don't even know, like I can hear, let's see. I don't know if this would show on the screen, but let's see. It's kind of like,
That's a little hard to
might be
see. Oh,
backwards.
let's see. Maybe I
Yeah.
can make you bigger. Oh yeah. Do that again. Now you're bigger on my screen at least.
Okay, let's see. I think, where is that number? Yeah, so like kind of at the very top here,
Right.
that's me. That's a minus I
Yep.
times
Yeah.
lambda. And then
Okay.
I'm trying to solve for this vector, and then that's my generalized, or that's my eigenvector from the lambda, from the eigenvalue that we found. And so
Ah.
I'm solving for that there. And then the algebra gives me some vector. I think I got 1, 2 for mine.
Uh-huh. Uh-huh.
And then here is my generalized solution.
Yeah, I see it. Yeah.
And
I-
it looks different because I have it's the
Yeah.
t times the eigenvector, but then we have to add the generalized eigenvector to it.
Yeah.
And then you generate your entire generalized formula. And then from there you can find C1 and C2, which I did there. And I got the right answer using that process.
Okay. I see. Okay, I'll tell you what. I do want to. I don't want to do this now. I want to go through this myself, just to make sure I understand the algebra better. And um, I particularly want to reconcile what the book is saying with why it's not working. Because your primary resource should be your book, and if the book is telling us to do the wrong thing, then we should figure out either how we're misinterpreting the book or if the book's wrong. Math books are sometimes wrong. So um, I'm worried this is a deeper issue. Probably I'm just misinterpreting what the book says in some way, and it's not quite as clear cut as what I think they're trying to say. So tell you what, let's postpone this. Let me get back to you on it, and I will, if I can't figure it out shortly after class and email you all, then I'll just I'll either postpone the due date on this particular homework assignment or just pull that particular problem off this homework assignment. Were there other parts of this homework assignment that had similar issues? This was problem 5. What about problems 1 through 4? Were they all straightforward?
I used probably the same resource as Robert when I was doing like the first 3.
Okay.
So like it was different from like what we did in class, but then like I found answers that worked. It's like basically a completely different formula, but I was thinking that they're somehow algebraically the same.
Yeah.
So I can like email you the link so we can look at it later.
Sure. Yeah, you might as well email it to me. We'll take a look at it. We'll take a look at it later.
Sure.
All right, well, let's move on. As I said, we're going to skip section 3.6 for now. 3.6 is a little bit of an anomaly to me. So I'll just tell you in 3.6, the authors go back to second order equations. We've been looking at first order linear systems. So in 3.6, they go back to second order single equations. And we learned earlier in the semester how to rewrite those as a 2x2 matrix. Take a second order equation and rewrite it as a first order system. And the point is, now that we know how to analyze linear first order systems, then we can apply that analysis to second order equations and see what kinds of solutions those get. And you get some interesting special cases. It turns out you can't get any possible solution that we've seen if you start with a second order equation. We're eventually going to come back to that material. We will cover it. I'm just going to do it out of order. We're not really skipping 3.6. We're just doing things out of order. So we're just skipping it temporarily. And we're just going to jump right to 3.7. And this will also serve as a nice review of some of the other stuff we did, because I know we're probably all a little rusty, especially if you did the homework assignment before break. It may be a week or two since you've looked at this stuff. So we're going to move on, okay? Hopefully you're still seeing the iPad screen. And I don't know if you're still seeing my video, your classmates there. I'm still seeing you guys on one monitor and my screen on another. So we're looking at systems. Oh, I'm in red now. That's all right. Y prime equals some matrix times the vector y. Right, these are vectors. And we want to treat this a little more generally now. Say, like, what's everything that can possibly happen? So there's two quantities that are super important. And let's see where they come from a little bit. The book doesn't do this. If we were to just solve this in general, the first step is to get the characteristic polynomial, right? So we need the determinant of A minus lambda, B, C, and D minus lambda. So we just solve that. I'm just going to do this completely generally now. A minus lambda times D minus lambda minus BC equals 0, right? And that gives us AD, I'm just going to use FOIL now, AD minus A lambda minus D lambda plus lambda squared minus BC equals 0. Okay, so that we can put that together, we get lambda squared minus A plus D lambda minus BC equals 0. Good, we're good so far? All right, and now we got to use the quadratic formula. So we've got, oh wait, I lost something. We're not good. You all lied. What did I miss? We've got plus, we missed the AD term. AD minus BC equals 0. Right? Now that AD minus BC term should look familiar. What's that?
Determinant?
Yeah, it's the determinant. Does anybody know, you may not know unless you've had a linear algebra class, even in first semester linear algebra, the term doesn't come up as much as it probably should. Does anybody know what that, if we look at the original matrix A, B, C, D, that quantity A plus D, it's the sum of the things on the diagonal there. That's got a name too. Anybody know what the name of that is? You add up the elements of a matrix that are on the diagonal of the matrix? No? That's called the trace. It's the trace and the determinant. The trace and the determinant are super important. So I'm just gonna do a little aside here. So whenever you have a matrix, those of you who have had linear algebra should have seen the idea of a similar matrix or a change of basis. So imagine I just draw a vector field. So we can do this in our language instead of the linear algebra language. So in our language, matrices represent vector fields. Okay, they represent the phase portrait. So for example, here's a phase portrait. Just kind of a generic phase portrait. I'll just start drawing things. Things maybe move along these lines, and these lines. Typical example of a saddle type phase portrait. Okay, now the one thing I didn't draw in this picture intentionally is I didn't draw any axes on this picture. I didn't tell you where the X and Y axes are. I mean, your eye probably said this is the X axis and that's the Y axis. Okay, but you could rotate your page. Maybe, I like all these colors. Maybe this is the X axis and this is the Y axis. Or maybe this is the X axis and this is the Y axis. Well, we've got all these choices for axes. That same phase portrait will be written down as a matrix with any of those choice of axes. In the linear algebra language, you say you pick a basis for the plane. A basis just means you pick two vectors. One's a vector in the X direction and one's a vector in the Y direction. Once you fix those basis vectors, then any picture you have in the plane, you can write down as a matrix. So if I pick the red vectors, then I get some red matrix, A, B, C, D. If I pick the blue vectors, I'll get some other matrix. I don't know, A prime, B prime, C prime, D prime. Okay. So the choice of representation as a matrix depends on your choice of basis vectors. But there's this really cool fact from linear algebra, which is that certain matrix quantities don't change if you change basis. And there's two in particular. So one of them you've already seen, which is the determinant. If you calculate the determinant for the red basis here, you calculate AD minus BC. That's the determinant for the red representation of this phase plane. And then you do it for the blue representation, A prime, D prime, minus B prime, C prime. The amazing thing is that these two will be equal. That no matter what matrix representation you pick for the same picture, you will get the same number for the determinant. The matrices may look completely different, but when you calculate the determinants, they'll be the same. And that's because the determinant is really capturing something about the geometric nature of this phase plane. It's not capturing the specific representation of it, but it's geometry. In the linear algebra language, if you've had linear algebra, you should have learned that determinant is a similarity invariant. So you say two matrices are the same if you can transfer your basis for one and do a change of basis to the other. That changes the matrix to a different basis representation, but certain numbers turn out to be similarity invariants. They don't change when you do that, and determinant is one of them. And there's only one other similarity invariant, which is the trace. It will turn out that the quantity A plus D, the trace in the red matrix, the sum of the things on the major diagonal, is the same as A prime plus D prime. Those are the same. Okay, and so that's why they get special names. The determinant comes up a lot. We've already seen the determinant in this class a lot. It gets a special name because it comes up so much. But the trace also gets a special name because it's the only other similarity invariant. And we see both these things now pop up in the characteristic equation here. In this equation, we see both the trace and the determinant. So we're just going to rewrite this equation for now as lambda squared minus the trace times lambda, so T is for trace, plus the determinant equals 0. So for any 2 by 2 matrix, your characteristic polynomial always looks like this. Lambda squared minus the trace times lambda plus the determinant equals 0. So let's just jump down here. I'm going to rewrite that. Lambda squared minus the trace times lambda plus the determinant equals 0. So again, you should think about what I just said about this phase plane picture, which is that the trace and the determinant, they are independent of your choice of basis. So now this equation right here, it only depends on the trace and the determinant. It doesn't depend on your choice of basis. So what this is saying is that the roots of this characteristic polynomial give you the eigenvalues, and that makes sense. The eigenvalues don't depend on their choice of basis, right? The eigenvalues are telling us the rate at which we move away from the origin on this axis up here, and the rate at which we move away from the origin on this axis here. And those two rates don't depend on whether or not I chose the red basis vectors or the green basis vectors. So it makes total sense that the eigenvalues are another thing that don't depend on the choice of basis, which means somehow they only depend on the trace and the determinant, which is why we're seeing that in the characteristic polynomial. The eigenvalues shouldn't depend on A, B, C, or D. They should only depend on similarity invariant quantities. This is very different teaching in front of you guys like this, because I feel like I'm just rambling at this point. So please stop me or slow me down. If I say anything that is confusing to you, just say something, okay? I'm just going to keep going here, though. We've got the characteristic polynomial, depends on trace and determinant. And now we've got to figure out what the eigenvalues are from this. So our only choice at this point, we can't tell if it factors if we don't know the trace and determinant. So all we can do is use the quadratic formula. So we get lambda is minus b, so that's the trace, plus or minus the square root of b squared, that's t squared, minus 4ac is 4 times the determinant, all over 2a is just 2. Okay. All right, so those are our eigenvalues. We've got lambda 1 is t plus that square root. And lambda 2 is t minus the square root. All right, so let's start thinking about some of this stuff in a more holistic way. So you guys tell me, somebody chatted or just turn on your microphone and yell it out. When are we going to get complex eigenvalues? Let's start with that.
When 4D is bigger than the trace.
Yeah, when the stuff under the square root is negative, then we'll get complex eigenvalues, right? So that's just telling us that t squared minus 4d is less than 0. And that gives us complex eigenvalues. That tells us that t squared is less than 4d. And another way to say that is to say that t squared over 4 is less than d. So if I take the trace, I square it and divide by 4, and I get something less than the determinant, then that tells me right away that I must have complex eigenvalues. Okay? All right. So we want to develop a picture of this. So we've got this equation t squared over 4 is less than d. So we're going to plot this in what's called the trace-determinant plane. So we'll put the trace on this axis, the determinant on this axis, and this is going to be a picture of all possible matrices. Every 2 by 2 matrix has a trace and a determinant, and so every 2 by 2 matrix is going to be represented by a single point on this plane. Okay? And now I want to ask, where are the matrices, where are the points in this plane where the determinant is greater than t squared over 4? So to answer that, let's plot the equation in this plane d equals t squared over 4, and then we can figure out which points have d greater than t squared over 4. So remember, d is on our y-axis, and t is our x-axis. T is our horizontal axis. So if you just think about the equation y equals x squared over 4, y equals 1/4 x squared. Y equals 1/4 x squared. You should all know what that looks like. Whoops. All right, y equals x squared is a parabola, right? So y equals 1/4 x squared is just a wider parabola. So if I plot d equals 1/4 t squared in this plane, then that just looks like a fairly wide parabola. That's terrible. It's supposed to be symmetric, but I'm drawing on an iPad. Cut me some slack here. All right, so there's the parabola d equals 1/4 t squared. So where are the places where d is greater than 1/4 t squared? Where is that in relation to the parabola?
That's above it, right?
Yeah, does everybody see that? Thumbs up, thumbs down? Good? Okay, cool. All right. So these points are all the stuff above the parabola. So again, if I have a matrix, I compute its trace, I compute its determinant, and I just check, is d bigger than t squared over 4? If the answer is yes, then that means that this stuff under the square root is negative, and that tells us that both my eigenvalues are complex, right? Now, hopefully you remember from before break, if you have complex eigenvalues, the picture is either we have a spiral sink, things are spiraling into the origin, a spiral source, things are spiraling away from the origin, or we have a center where things are just going in circles around the complex plane, around the phase plane. How do we tell? How can you look at the eigenvalues and just tell whether or not you have a spiral sink, spiral source, or center? So I tell you right away that the eigenvalues are complex. That tells you that this thing here is negative. How would you look at this expression, this whole expression, and determine whether or not we've got a spiral sink or a spiral source?
Someone said something in the chat.
Values of A. It's a little more complicated than that. Values of something will tell you. Just look at this expression I've circled in blue, right? So what in this expression tells you if you have a spiral sink or a spiral source?
It should be the real component of the.
Oh, Robert, when you said A, did you mean like if I have my eigenvalues look like A plus BI?
Yes, sorry.
Yeah, no worries.
Yeah,
No worries.
if that's if
We're
positive.
using A all the way up here to be this first component of the matrix, right? Yes, it's what you said exactly right. Normally we write the eigenvalues as A plus or minus BI, right? And it's the A part. What Robert said is exactly right. It's the A part. It's the real part that tells you if a spiral sink or a spiral source, and that A part is exactly T. It's not quite T. It's T over 2, right? Because we've got this 2 in the denominator. So 1/2 the trace is the real part, and if we have a spiral source, then how can we tell that from that real part?
If the real part was positive, right?
Yeah, positive, right. So if T over 2 is positive, we know I have a spiral source. If T over 2 is negative, we have a spiral sink. And we're going to get those nice centers where things move in circles when T over 2 is 0. The 2 isn't going to change whether or not T over 2 is positive. So a simpler way to say it is just if T is greater than 0, we have a spiral sink. Source. If T equals 0, we have a center. And when T is less than 0, we have a spiral sink. All right, now let's just look at these cases individually. Where in the picture, so again, let me just reiterate where we're at. All the red stuff is the stuff where we know we have complex eigenvalues. So just looking at the red stuff, the stuff above the parabola, where on that red stuff is T greater than 0?
To the right-hand side.
Yeah, Ezra said it too. Good. Yes. So this is where T is greater than 0 is right here. Okay. So those are the places where we have a spiral source. What about T equals 0? Where's that?
On the d-axis.
Yeah, T equals 0 is right on the axis. That's this stuff right here. And then T less than 0 is everything that's left, which is over here. Okay. So this is where we're at so far. If we have any kind of matrix at all, and you compute the trace and the determinant of that matrix, then you can identify where that is in this trace-determinant plane. And if you find that that represents a point on the top right here, then here you must have a spiral source. And over here, you'd have a spiral sink. And over here is where you have these center tangencies. Okay, so we get these, we're going to identify points in this plane, this trace-determinant plane, with little tiny pictures of phase portraits that correspond to those points. Okay? Let's keep going. What about, there's an easier case. What about looking all the way back here, here are our two eigenvalues, right, given by this expression, t plus or minus the square root of t squared minus 4d over 2. If I'm not above that parabola, then now I'm back to having real eigenvalues, right? They're not, as long as I'm not in that red area, I'm not above the parabola, then I know I don't have complex eigenvalues. But now there's a lot of other cases. We could have two positive eigenvalues. So that would give us a source. We could have two negative eigenvalues. That would give us a sink. We could have a positive and a negative that gives us a saddle. We could have a zero eigenvalue, or we could have repeated eigenvalues, right? So let's identify where in this trace-determinant plane all those different pictures are. So I think the next easiest case is when we have a positive eigenvalue and a negative eigenvalue. So one of these is greater than 0, and one of these is less than 0. So let's rewrite what's going on down here. We've got lambda is t plus square root of t squared minus 4d over 2. And we're going to assume that one's greater than 0. And t minus square root of t squared minus 4d over 2. We're going to assume that one's less than 0. Okay, one's positive, one's negative. And we're going to try to figure out where in this plane we have to be in order for that to happen. Okay. What if they're equal? Let's do that first. Sorry, instead of doing this, well, what if these two things are equal to each other? So here's lambda 1, lambda 2. What if lambda 1 equals lambda 2? Then what do we know?
Repeated.
Is it
Yeah, then we have a repeated eigenvalue, right? Where does that happen? Oh, I see it. Anna's saying it. T squared, good. T squared minus 4d equals 0, right? And this part of it equals 0. That's good. All right. So that tells us that's the easiest case. So I want to do this sort of increasing levels of difficulty. So where is t squared equal to 4d? Another way to say that is, where is d equal to t squared over 4? Somebody said, oh, Anna had said on the d axis. It's a little more complicated than that. Where's t squared equal to d? T squared over 4 equal to d. Somebody just want to chat it? On the parabola, good. Yeah. Good, Michelle said it. Yes. That's exactly these points on the parabola. So on the parabola, we have repeated eigenvalues. There's a couple different cases for repeated eigenvalues. And again, that's the one, exactly the homework problem that I flubbed a minute ago. So that's the hard case, right? If you have repeated eigenvalues, then there's actually two different possible pictures. One case is that everything just radiates out from the origin in all directions. That's the case where every vector is an eigenvector. And then there was another case where you just have a single line of eigenvectors, and then you get this sort of characteristic S-like thing. Right, so if you have repeated eigenvalues, then it can look like one of those two pictures. But there's still a concept of sink versus source. So how do we tell that? Well, let's say t squared, let's say we have this, we're in this situation, and we want to know, is it a sink or is it a source?
Is it the sine of lambda?
Yeah, the sine of lambda. What's gonna, so if this thing under the square root is 0, then what determines the sine of lambda?
That's trace.
Yeah, just the trace, right? Just the trace. So if the trace is positive, we have a source, and if the trace is negative, we have a sink. So I screwed up here. This stuff right here corresponds to the stuff on the right side of the parabola. And the pictures are exactly opposite on the left side of the parabola. Right? On the right side of the parabola, that's where t is greater than 0. And t greater than 0, now if I'm on the parabola, that tells us the stuff under the square root 0, so I have repeated eigenvalues. And if I'm on the right side of the parabola, then t is greater than 0, and that tells me I have a source. And if I'm on the left side of the parabola, that's going to tell me that all those arrows are switched and I have a sink. Okay, so we have those two possible pictures on the right side of the parabola, and then two similar pictures on the left side of the parabola. All right, let's look at the case now. Let's go back to the one that I started to talk about a minute ago. What if lambda 1 is greater than 0 and lambda 2 is less than 0? Let's think about that case. So we have damn, I keep wanting to do that case because to me that's the most interesting case. And then I keep thinking, well, you know what? That's actually the hardest case. let's do them both greater than 0. Sorry. Let's do lambda 1 is greater than 0 and lambda 2 is also greater than 0. So if you look at lambda 1 up here, let's just assume for just a minute that t is positive. Okay. So t is positive, then this stuff will always be positive. Does everybody agree with that? If t is positive and we're not complex, since I have a plus sign here, then that whole quantity has to be positive. Okay, so as long as you know t is positive, then the way you get this one for free, right? T greater than 0 gives you lambda 1 greater than 0 for free. The thing you have to worry about is whether or not lambda 2 is also greater than 0. So again, I'm just thinking about what happens when t is positive. And now we're going to look at lambda 2 and say, when is that thing positive?
That's when what's under the square root is smaller than t, right?
Yeah, we can just do the algebra, right? If lambda 2 is greater than 0, let's just write it out. We have t minus the square root of t squared minus 4d over 2 is greater than 0. Okay, you can multiply both sides by 2 and then add the square root to both sides. So when I multiply both sides by 2, the 2 just goes away, right? It gets killed with that 0. And now we get t is greater than the square root of t squared minus 4d. Okay, now we can square both sides. That gives us t squared is greater than t squared minus 4d. Okay, keep going. Let's subtract t squared from both sides. That gives us 0 is greater than minus 4d. Okay, and now I can divide both sides by -4, and just keep in mind when you divide by a negative and you have an inequality, it flips the inequality. So that tells you that d is greater than 0. So as long as lambda 2 is greater than 0, then d is greater than 0. And we were assuming through all this that t was also greater than 0. Good? All right. So we get so this is what we've got to plot, is the places where d is greater than 0 and t is greater than 0. Where is that in this picture? D greater than 0 and t greater than 0. That gives us two distinct positive eigenvalues, right? They're not the same. We already did that case. The same eigenvalues means we're on the parabola. So if we're not on the parabola and both are positive, then where are we? Okay, good. Ezra said first quadrant. Yeah. This is the place over here where we have sources. Let me draw a better picture, actually. So what things look like here is we have two eigenvalues in two different directions. Things move away from the origin. And then since they're distinct, off of the eigenvalues, things move along these parabolas. Okay. All right. Now let's look at the opposite. If t were less than 0, right? So let's forget about this assumption. Now let's look at the case where t is less than 0. And I want to say, when do I get two negative eigenvalues? So again, if t is less than 0, then lambda 2 is automatically less than 0. And I have all this algebra I can do to say, when is lambda 1 also less than 0? And I'm not going to do it because you're going to just make a guess. Where do you think in this picture I'm going to get two negative eigenvalues?
In the third quadrant?
Try again. Everything's symmetric, right? So we got two positive eigenvalues
Second quadrant.
to the right of the parabola. So to the left of the parabola is where we're going to get two negative eigenvalues. Yeah, it's over here. So here we're going to get sinks. Things move toward the origin. We have two distinct eigenvalues. Those are going to correspond to two distinct eigenvectors. And then away from those two, things will move along parabolas toward the origin. Okay. So actually, there's a nice picture here, right? Even if you just think about what's happening both inside the parabola and outside the parabola, as long as I'm in the positive quadrant, both those cases are sources, right? I've got a source here and a source here. One of them is a spiral source and the other is just a regular source. And in the second quadrant, I've got a sink and a sink, right? So there's a lot of ways to say what's going on here. The parabola is dividing the spiral stuff from the non-spiral stuff. And the quadrants are telling you if you have spiral source, spiral sink. Okay? And the one case we haven't dealt with yet, the one big case we haven't dealt with, is when we have a positive and a negative, but there's not a whole lot left to figure out what's going on when you have a positive eigenvalue and a negative eigenvalue. Where is the rest of the plane? What else is happening? Well, the only places we haven't filled in is the stuff below the axis here. And there's only one real case left. All this stuff down here, that's when we have saddles. There is one more case we haven't talked about, which is actually what happens on the t-axis itself. What is happening on the t-axis?
The determinant is 0.
Yeah, good. That's the determinant is 0. Let's look at what happens when the determinant is 0. So we got t plus or minus the square root of t squared minus 4d over 2. And we're going to think about what happens when the determinant is 0. So that gives us t plus or minus the square root of t squared minus 0 over 2, which is t plus or minus t over 2, which is two solutions. We get 2t over 2, and we get 0, right? So that's t and 0. So when the determinant is 0, that's the case where we get a 0 eigenvalue. And actually, one thing that I don't think we've said before is that whenever you have a 0 eigenvalue, the non-zero one is the trace. You can easily figure out the non-zero one just by adding the things in the diagonal. That always gives you the non-zero guy when you have a 0 eigenvalue. Okay, so the picture when we have a 0 eigenvalue, those pictures are going to happen on the t-axis itself. So we can draw that in. Oops. Those are the cases where this picture's getting too small. Let me make it bigger. I'm going to redraw the whole thing now. Okay, so again, we've got our trace axis, our determinant axis. We've got this special parabola. It's a little nicer. Okay, on the d-axis, where t is greater than 0, that's where we see these center tangencies. Okay, they either spiral clockwise or counterclockwise. We can't tell that from this picture. That you have to do some work to figure out if it goes clockwise or counterclockwise. I'm just going to draw it as counterclockwise, but it doesn't matter. Above the parabola, to the right of the d-axis, those are the spiral sources. And to the left of the d-axis, those are the spiral sinks. Okay. On the parabola itself, we've got two possible pictures. Those are the repeated eigenvalues. So there's two pictures. One is that things move directly away from the origin in all directions. That's when you have every vector is an eigenvector. And the other possibility is that you've got a line of eigenvectors and these S's. Okay. And then something similar is happening on the left side. We've got, again, everything's either moving toward the origin or things are moving along a line toward the origin and along S's. Okay. In the remaining portion of the first quadrant, that's where we've got two distinct eigenvalues. Okay, but they're distinct, and so that we get these parabolas where things move along. And on the other side, we've got two distinct negative eigenvalues. Things move on parabolas toward the origin. Right. Down here on the entire bottom part of the picture, whoa, stop that. Stop that too. The entire bottom part of the picture, everything down here. So I'm gonna, what am I gonna do? I want to white that out. Well, I can't, doesn't matter. Down there here in the entire bottom part of the picture, we've got one negative eigenvalue, one positive eigenvalue, and everything else moves along hyperbolas. Okay, and then on the t-axis itself, that's where we have a 0 eigenvalue, and we can still have two distinct non-zero eigenvectors. And if you remember what that looks like, the 0 eigenvalue corresponds to sorry, the non-zero eigenvalue, sorry, I'm really misspeaking a lot today, I apologize. The non-zero eigenvalue corresponds to an eigenvector where things move, on this side of the axis, things move away from the origin. The zero eigenvalue corresponds to an eigenvector where you have this whole line of fixed points. And then everything else moves parallel to the non-zero eigenvalues eigenvector. So things move like this. I know that's all very confusing. Okay, so that's the picture of what's happening on the right side of the t-axis. And then on the left side of the t-axis, we have something similar, except things move toward the origin instead of away from the origin on one direction. On the other direction, we still have this line of fixed points. And everything else is moving toward that line of fixed points in a fashion that's parallel to one of the two eigenvectors. That's what's happening for all the points on this axis here. And it turns out there's nothing special about the vertical axis below the horizontal axis. The place where d equals, so d is less than 0, but t equals 0, you may wonder, like, what's going on over here on this axis here? And there's nothing particularly special about that. And again, we can see that. Let's just look at this quantity one more time, t squared minus 4d over 2. On this place below the t-axis, that's where t is equal to 0 and d is less than 0. And there's nothing really special about that. If t equals 0, if t equals 0, then we get 0 plus or minus the square root of 0 minus 4d over 2, okay? That's just plus or minus the square root of negative 4d over 2. That's just plus or minus square root of negative d. Right? Because the 4 can come out of the square root and becomes a 2, and then that cancels with the 2 in the denominator. Now that looks like it should be complex, but it's not, because d is negative. So when you negate d, it becomes positive. And when we take the square root, we just get a number, and the eigenvalues themselves are the positive and the negative of that number. And so that just tells you you have another saddle. It just tells you that this is the correct picture, even if you're on this axis. So being on that axis below the t-axis doesn't tell you anything. Above the t-axis, it tells you you have one of these centers. But below the t-axis, there's nothing really special about it. Right? So really what's happening is we have these dividing lines. We have the t-axis itself as a dividing line, the parabola as a dividing line, and then the positive d-axis is a dividing line. And you should know what happens in every one of these regions. You should know what happens here, where everything's below the t-axis. Those are the saddles. Here, these are the sources with distinct real eigenvalues. The sinks, spiral sources, spiral sinks, and then on those curves themselves, you get these weird interface cases. On this curve, we have the centers. Here we have the repeated eigenvalue cases where they're both positive. The repeated eigenvalue cases where they're both negative are here. And over here, you have the 0 eigenvalues where the other one is positive. And here you have a 0 eigenvalue where the other one is negative. Okay? This picture you really should just have memorized. And it's in your book. If you look in your book, you'll see that picture as well. In fact, it's on page, let's see, page 351 of your book at the top. And they drew it much nicer than I could draw it. It's figure, so if you have your book in front of you, you might as well flip to this, figure 3.48. You'll see this nice diagram. So the nice thing about this now is I can just throw any matrix at you, and just by computing the trace determinant and identifying where it is in this plane, you can tell me what the picture is right away without doing a whole lot of work. We just keep reducing the amount of work. So here, I'm just going to start making crap up here. I'm going to make up a matrix, right? 2, 1, minus 3, and 6, no, 4. Good. All right. So what's the determinant? Real quick, somebody type it in the chat. We'll see who can get it first. Awesome. Anna says 11. Good. What's the trace? Even quicker. Somebody. 6. Good, Michelle. 6. All right. So now we got to figure out where we are in this trace determinant plane. We've got to plot 6, 11, trace determinant. We want to plot the point 6, 11. So we're definitely somewhere in the first quadrant, okay? It's not quite so easy to tell where in this, where in relation to the parabola it is. Is it below the parabola, above the parabola? It could be this, it could be the picture, or maybe this is the picture here, or maybe the parabola goes right through that. How can we tell? We can do a little computation to tell where we are with 611 in relation to that parabola. Remember, the equation of that parabola was d equals t squared over 4. That was the equation of the parabola. So what do we do with that to tell us where we are in relation to the parabola?
If you plug it in and then check the inequality on both sides and see which side you're
Yeah,
on.
we just want to plug it into both sides, right? So the determinant is 11, right? And then t squared over 4 is going to be 6 squared over 4, which is 6 times 6 is 36, divided by 4 is 9. Did I do that right? 9? 9 times 4 is 36? Yes, good. All right, what's bigger, 9 or 11? That was a stupid question, I'm sorry. 11 is clearly bigger than 9. I don't want to insult your intelligence, right? So if we get that d is bigger than t squared over 4, that tells us we're above the parabola, okay? As long as d is bigger than p squared over 4. So actually, it is a really wide parabola. The parabola does look like this. That point's above the parabola because d, for that particular point, d is bigger than t squared over 4. And so what kind of system is this? How would you classify the equilibrium point in this system? Just chat it. Somebody type it out. Spiral source. Thanks, Ezra. Good. See you, Robert. Good. These points here are all spiral. Everything there is a spiral source. Good. So you see how this works? Is it really 12:30? Did I just go 15 minutes overtime?
Just a little bit.
Shit, I'm sorry. I need like an alarm because I'll just keep babbling. Nobody said anything. Somebody's got to say something. Thanks, Amber. All right, let me just say one very, very, very quick thing before you go. I'm going to share my desktop, I guess. So now hopefully you're all seeing my desktop. Are you all seeing yourselves?
What?
Oh, here, let me, actually, I want to share something different. Share this. Share. Are you seeing my WebWorks screen?
Mhm.
Okay, good. All right. Crap, I've already gotten logged out, so let me fix that. Homework 11 is posted. It just opened at noon, and I want to just show it to you real quick. I don't normally do this, but if you look through the homework 11 problems, they are problems that I've already assigned you, but I want you to redo them and do them differently. So here's the first problem. You've already done this, and you did it hopefully by actually doing the eigenvalue computation and then seeing what you get. Now I want you to do this differently by just computing the trace and determinant for each one, figuring out where you are in the trace determinant plane, and that'll tell you whether or not it's a source or a sink or a saddle or what. And then that should tell you which picture it is. And there's only 3 homework problems, and they're all ones I've given to you before. There's the next one. Again, just same thing. Just use the trace determinant plane, figure out where you are in the trace determinant plane, and use that to figure out what the right picture is. Okay? It's just a little practice for you. Good? All right. Let me know by email if anything about this process did or did not work for you. Well, specifically, let me know if anything didn't work for you. Let's just say that. If you have any suggestions for how we can improve class, other than me keeping track of time and not going over by 15 minutes. All right.
Thank you.
One other thing, I hope you all got my email. My office hours have changed. They're now Monday and Wednesday morning, right before this class, from 9 to 10:30. They used to be Tuesday and Thursday. So I will be on Zoom sitting here from 9 to 10:30. Feel free to just chime in anytime and ask a question and leave. Okay, good. See you Wednesday morning.
Thank you.
Sure.